Hi, I hope you're having a good day. This is Dr. Sheets. Well, today we're going to talk about distributed database management systems. And it's a whole world of complexity on top of the things that we've learned so far this semester. The idea that we would have, instead of just one database, the difficulties and complexity that we have with managing one database, that we would need to distribute that database. In other words, make it in more locations and add dramatically to the complexity associated with our data management. Shows how important it is to adapt to business situations. Certainly you would never have a distributed database when you didn't really need one. You wouldn't do it just so you had the opportunity to develop a distributed DBMS system. Well, so that's what we're going to talk about today. And we're just going to learn about what are the major pieces of a DDBMS, how the implementation things are different whenever you are worrying about this distribution idea. Talk a little bit about transactions. If you think about concurrency management and how difficult the locking process is to make sure that everything works fine in a centralized database, you can imagine if you have at least two, but maybe 3, 4, or 5 where the transaction spans across multiple databases, you can see where that's going to be harder to control the locking and the concurrency that goes along with it. Well, and then we'll talk a little bit about some of the ideas associated with how to design a database, and there's some interesting things there, I think, on fragmentation from a design perspective. Well, what happened is the data got to be too big, and the needs got to be too geographically distributed, that the central database wouldn't work anymore, right? And so what's happened is the networks have provided us this ability to distribute these systems, but it also gives us the ability to make systems that are much more complex and more difficult to manage and maintain. So, but a distributed DBMS must do everything that any centralized database must do, and it is just more difficult because it is spread across more sites. Well, so here's our little world that we've been working in all semester, where we have an end user and they talk to the database and get back their results. Web is slightly different, but this is basically the process. We send our request to the DBMS, even if it gets filtered by the web server and all that. Then the DBMS sends back our results set. It's a nice, simple little world. But the problem is that world doesn't always fit with the way what the business really needs. And so what we have is this idea that we need to distribute, at the very least, our process. And that's where things usually get started. Because here we have a site in New York and another site in Atlanta. Well, we need these sites, right? Because that's where our customers are. That's where our work is occurring. There's no way we can't have our organization in this location. So we have, luckily, or now, the communication networks capable of supporting this kind of distributed work. And so this is distributed processing, where you have processing occurred at many different locations and the database stored in one location, in this case Miami. So that's the idea of distribution. It definitely involves a geographic component. Well, the things that sort of made all this possible is we are so much more connected globally than we ever have been. And so operations need to occur in the places where people are. And it's just been the way of the world for so long that that's what has to happen. And so this geographic complexity that we didn't have before was sort of, I believe, enabled by all of our network technologies. And so by now that we have both the ability and the desire to be in these locations, it's generated a whole new level of innovation and the creation of data and the creation of opportunities that are truly dramatic. But this is what led us sort of away from only centralized databases to a more distributed idea. Well, and then as we move on, the idea that internet is where we are going to do business today. I mean, many systems, even if they are systems internal to organizations, are built on a web platform, right? So the internet as a concept and things has really evolved and really become sort of a dominant perspective in deploying applications. Of course, now we're moving into the new world of wireless apps and things, and we're just, I think, in the beginning of all that as to be able to see where we're headed in terms of mobile devices and the kinds of applications that we can use. Well, and we're also moving on to this idea that we're not just have data, right? What we have are information and processes that can be used to really make more informative decisions for the organization, and that's I think where we're really headed. Well, the problems that we have with centralized systems, where mostly in my mind we're going to go distributed because of performance problems, right? Something is telling us our centralized system isn't going to be able to be scalable. Then we're going to have to come up with something else. And another primary issue is reliability. We need some way to guarantee our 100% or 99.999999 uptimes, right? And the only way we can really do that is to have replications of our data. That's the only way we can really be guaranteed to have that guaranteed uptime. And so in these situations where you have the need, the distributed DBMS has a capability. So some of the advantages are the data. You get a faster access because the data are closer to the people that are using it. Ideally, you've set up a situation where as things grow, they're consistent with the growth of the organization. So the ability to continue to grow and to pay the cost of continued growth should be consistent with the organizations that are generating more, or the parts of the organization that are generating more revenue. There's the major thing is the less danger of a single point failure. That's a really important idea, is that we now have this thing that's going to always be up because we are designing it so that it will always be up. Now, you can ask yourself, how important is that whenever our centralized databases have already been at the 99.9 uptime level, but it is something that's important. But nothing comes for free in computer science. Everything is a trade-off. So we're going to have, it's going to be harder for us to manage this system. We're going to have a more difficult technology to deal with, more difficult transactions to write, more design decisions to make, like what kind of fragmentation we want to have. We need to have our people trained to be able to do these things. And so there's a lot of additional cost. So you have to be in a situation where you really need the benefits before you're going to undertake all these costs, in my mind. And of course, I'm going to be probably driving this off of performance, where my geographic locations will be driven off of my business plan or business practice operations. But my data distribution and those ideas, allocation and where I'm going to store my data, are going to be driven by performance. So if I'm able to perform with a centralized database, I'm probably not going to consider a distributed database. Well, we have two concepts. Distributed processing is when the programs are in different places. So you have one program in Atlanta, another program in New York. And both of those programs have processing to do, even though they could come from the exact same database. Now, the other idea also has the idea of distributed processing, because there would be no reason to have a distributed database if you had only centralized processing. But so the distributed database is not just the program that is distributed around geographically. It is, as in distributed processing, it is the database is also just distributed geographically in some way that is on different physical sites. Well, so the functions of a DBMS, or the distributed part of the DBMS, is to get the request in the same way similar to other DBMS, then of course validate the request like a parser and the optimizer do in the regular DBMS. Then it has the extra task of mapping the request to the distributed sites, and then working on I/O plans for those individual sites. And then it has to ensure the overall consistency and security, and then finally put it into the right data format and return it to the user. Well, so here's a example of a distributed database environment. See that we have a database at each of the sites, right? So the database is distributed, and if you can just imagine that if this is the HR database, there's some parts of the employee table, what we call a fragment of the employee table, in Miami, a different fragment of the employee table in New York, and a third fragment of the table, the employee table, in Atlanta. And so this would be a way of, or an example of, a distributed DBMS. And it would, or a distributed database, and it would also be distributed processing. Right, because here we would have multiple processes, we have multiple sites. There would also be distributed processing in addition to distributed database. Well, all the stuff that you need to have for a normal DBMS, you need to have for a distributed DBMS, and so there's going to be some kind of sophisticated management information system or information system on top of it. There'll be application interfaces. There'll be a whole series of things that you need to create a true information system. And this system will be more complex than one that doesn't rely on distributed data. Of course, some of the more important characteristics are the backup and concurrency control and transaction management. That is really key in our database world, as we've seen in previous chapters. So this idea of what all the distributed system has to do, it is everything that the centralized system has to do, but in addition, take care of the mapping of the different locations and fragments of the database, into taking those into account when creating transactions and processing queries in any of those activities. Well, there's so it must do everything the centralized database must do. Then it also must do the additional things necessary for distribution, and those things are complex. Well, so sort of the simplest way of seeing our distributed database is as a single database. Now, here we have two fragments. We have fragment A1 and fragment A2. But the way we think of it when we are designers and we're writing our program, we don't think about the individual fragments or where the database is. That is the idea of distribution transparency. So we don't really need to know when we execute our query that it is going against the database fragment that's A1 or against the database fragment as A2. It is our conception of the distributed database is this one logical database. Database. Imagine if you have an ER diagram, you don't even necessarily know what parts of what tables are stored in what locations, and so that is the way that you look at the data when you are trying to develop a piece of the system. Then once you have that piece of the system, that might help you to then decide what fragmentation should occur, and then implement the right stuff. But so the logical idea is here we have multiple processors, so distributed processing, and then we have multiple databases, so we have a distributed database. Well, just about everything you need for a normal information system you need for a distributed system, except you have these other two important components of the transaction processor and the data processor. The transaction processor is the thing that does the distributed processing. It's software that executes all the application system requests and then does the transaction from the perspective of the application. Think of it as a use case or something along those lines. And then there's a data processor that serves the data to the transaction processor that is the program that is trying to perform, where the user is trying to perform some task. Well, single site processing, single site data, that's our centralized world, right? That's the simplest possible database. And often our dumb terminals have now been replaced with a PC on the other end, but it's a PC acting as a dumb terminal, just sending requests to the database and receiving those requests and executing them. So here's our world. Life is easy, simple. We can have our terminals connect right through directly by hardwire to the processor, or we can have some sort of remote line. But the idea is there's one database and all of the processing actually occurs on that same computer, and there's only one of them. Well, multiple site processing, single site data. That's when we have many different sites and we use a network to connect them to one single database server. And so the potential here is that we can now be where we need to be from a business operation perspective, have people there, organize our business that way, but still we can keep our data on one single server. And then that makes things much simpler. And I think you'll see a lot of systems that are more distributed systems that are distributed processing, multi-processing single-site data than you will the true multi-site processing and multi-site data. Well, so this is the basic idea. Here we have our database server, and then we have our different locations all connected over the internet or some other type of network so that we can process the data and keep the data on one server. Now, I mean, if we just have another database server with or a total set of disk mirrors or something that we are using to provide replication of our file server, it's really still a single site data perspective. Well, this is the real distributed DBMS. It's multi-site processing, multi-site data. If you have multi-site data, you have multi-site processing. It wouldn't make much sense to go to the step of having a distributed data and not have a need for distributed processing. That wouldn't make much sense. Well, if you have a distributed DBMS, it can either be homogeneous or heterogeneous. Homogeneous means it's all from the same vendor, essentially, right? You have Oracle in New York and Oracle in LA and Oracle in Atlanta. And you have the same table names in all three locations, but in one location you only have the New York data, and the other location you only have the LA data, and the other location you only have the Atlanta data. Even though all the table names and the column names and all that stuff is exactly the same. So that would be a homogeneous distributed DBMS because it only uses the one vendor. But a heterogeneous distributed DBMS would mean that you have other DBMSs like Oracle or DB2 from different vendors that are also being used together. Meaning you're storing some of your data for your application in DB2 and other parts of the data for your application are stored in Oracle. Certainly it's possible that these kind of things could evolve in organizations. It's also possible that you might design a particular structure like this, given that you know what the demands are going to be at different levels in the overall system. Or not the overall network system, but the software that you're writing. Well, some DBMS that is fully heterogeneous might have different vendors, but also be different models. Maybe they have a relational or an object model, object-oriented database behind their model, as opposed to a relational. Or we have both an object-oriented model database in our system along with our relational database, so that we really have different ways of looking at the data. The more different things we have, the more complex our programs become and everything else becomes. And so we have to do this when we have to do it, but we want to be careful and only do it when we really need to. So here's a little example about the different types of DBMSs we might have. Right, so we were trying to take DB2, Informix, and Oracle, and we're going to have parts of our application in all three of these databases, and then we're going to be writing a transaction that runs across all three of these databases and 3 different computer platforms, right? If we're doing this, we better have a really good reason for designing our database this way. Yes, this is a heterogeneous database, and the question is, why would we want to create some system like this to solve a problem that could possibly be solved by any one of these database technologies? Well, when you are doing distributed databases, you don't want people to know necessarily that there's a bunch of distributed stuff behind what they're doing. To any one particular user, it should just look like they're they're the only user in the world, like they're the only one using the system. It should be transparent, or invisible is what the term should be to me. It should be invisible to the user where the data, how the data is distributed, what type of fragmentation strategy we use. It should be not matter at all how a transaction was formed. It shouldn't matter whether a node fails. The user should never know what different types of databases are involved in their transactions. There's just no need for that. And so this idea of transparency becomes really important in the distributed database world. Before, right, we always said we didn't necessarily need the user to know what tables, we could create a view that combined tables to make the user's perspective on the world easier to understand. But here, what we're hiding is complex enough that users would not find it very understandable. So this is the idea. We want to make sure that we're not imposing knowledge on our users, meaning that we don't want to make sure our users know things that they wouldn't normally know to be able to use our system. Well, so distribution transparency is the idea of fragmentation and location. And so the idea is with fragmentation, which we'll talk about a little bit here in a minute, we might have rows of one table in one location and other rows of the same table in a different location, right? That shouldn't matter to the user. They're being able to get the data they need shouldn't matter how the data are distributed. The user shouldn't have to know anything about it. Shouldn't have to know where their data are located, and they shouldn't have to know how to map from their local view of the data to the data at the distributed level. So from their perspective, every row is unique, regardless of where it is. When they get a row, they don't need to know where that row comes from. And that's what we have to maintain to have distribution transparency. And we do that through these sort of amped up data dictionaries or system catalog like we had for the centralized system. And under the creating and maintaining these systems adds another level of complexity and difficulty to the data dictionary and catalog processes, which I think you can see. So every time we take a step down this distribution road, we are increasing our cost. Well, and this last bullet here is on that idea of, I think your best way to look at the world is as one ER diagram and not even know anything about how the data are distributed, and then solve your query that way. And then after you have the correct answer or the right steps to get to the correct answer, then you can then think about revising it to take advantage of close data or things like that. Those are true low-level design or implementation level decisions for every one of our programs. Well, here's the idea of both fragment and location transparencies. I mean, if I write a query, I shouldn't have to know if my data are in E1, E2, or E3. It doesn't matter what fragment there is. I'm saying, give me all the employees under the age of 50. And it shouldn't matter to me. I shouldn't have to specify anything special to make you get all the employees under 50 from all of my different locations either. Right? It's just saying, the transparency is just saying that you don't have to know that when you are writing your query. But when your query gets executed, it will take into account all those things. Well, transactions are, again, another level of complexity. I have a couple slides down here later on how transactions work in the distributed world. But trust that it's more complex than the locking and concurrency control processes in a centralized system. Well, there's several types of remote interactions with the database. The first is just a simple SQL statement. You know, maybe it's a query of some sort. A transaction, which we're already used to, is where a series of statements are executed and they have to either all succeed or all fail. Well, now a distributed transaction is where it's the same idea, except that if it fails in its work on one of the distributed systems, then it must fail in its work on all of the distributed systems. That means we're trying to access the data from multiple points at the same time. Right, and we have to maintain the consistency of our database across those transactions. And then finally, distributed requests are when a single statement actually brings data from many different sites, and that's what we see when we have fragmentation. And part of our table is in one location, part of our table is in another location. And we want our data to come from all three locations, even though we didn't specify that when we made our query. Well, if you thought concurrency control was a little bit complex in the first step, where we talked about how deadlocks could occur and when the concurrency and how transactions have to commit or roll back, I think if you start thinking, it doesn't get too long down the road, you get to the ideas like, well, suppose I commit in one location, but then in another location, something happens and I have to roll back, but I've already, and so you can see, just sort of trying to think through it logically, it's a pretty complex process in the distributed world. So here we have a transaction, right? So we're in site A, we make our lock, and we make a commit. So now once we've committed, we can't roll back. But another part of our transaction, which is taking place on C, has to be rolled back. And so we have a problem. We have a problem that we don't ever want this situation to occur. And so we have a plan, and it's the two-phase commit protocol. And what it really means is that we're going to write the log to the database before we write the data to the database. Now, often we do that, we write the log second, right? But what we want to be able to do is provide this ability of do, undo, and redo. so that as necessary and automatically we can roll our transactions backward and forward with using our transaction log. And that's something that we don't normally do live in runtime. We usually use those routines that roll forward and back, and when there's a problem and we have to recover. But here, what we're saying is we're going to take the chance. We're going to make a commit on the log, showing that we've done the work, and then if we have to, we will undo it and redo it if there's a problem with the final commit. And so the two phases is first there's a write-ahead process, which is the preparation of the transaction to be committed. And so essentially what we're looking for is to get every different site to say, I'm ready to commit, I'm ready to commit, I'm ready to commit, and then for a site to hit the final commit. And that sort of makes that process between the final commit and knowing that everybody in the set is ready to commit is the important thing. So we write ahead our log entry so that if something happens along the way before we actually write our data, which is going to be the final commit, then we are in a position to know what we were going to do and then be able to roll it back. Well, the performance is the idea that you shouldn't know you're on a distributed DBMS. It should be just as slow or fast as a centralized system, and so you shouldn't be able to know that. Failure or failover is one of the important things in many organizations, such that you have the ability for when some failure in some part of the system happens, the user never really knows that failure occurred because there is some other resilience in the system that are able to pick up the traffic in a fairly seamless way, meaning that the request to the downed item is just redirected easily to one that is available. Well, we have when we are responding to a request, our most important thing is how are our data distributed. But a lot of times in these worlds, we also have data replication. And sometimes we can leverage our data replication to increase our processing speed and our performance by having parallel tasks or multiple tasks operating at the same time rather than having those tasks operate in sequence. Well, the user also shouldn't have to know anything about how the network is working, whether the data are on one particular node of the network or whether the processing time is delayed due to some sort of network latency. But this is, to me, sort of it's important because there can be no distributed system without the network. And so whenever problems happen with the network, and there will be problems that happen with the network, anytime that you build the network into your architecture, there's going to be problems, so you have to have a plan for handling those problems. So the point is the user should never know if there is some sort of network node failure, perhaps unless it's their own node. Well, this is the part that's most interesting to me, and it is the design process as more of a developer versus DBA type, this is the things I think are interesting. Like data fragmentation to me is the most interesting distributed database idea. And it's not that sophisticated, but it's kind of interesting. It just says, where do you put what parts of the data? Once you've just decided to do distribution, where will your pieces of the data exist? And if you had decided to do distribution, it's probably due to some need to fragment the data for performance purposes. Well, then we also do a lot of data replication these days, because that's what really gives us our failover capability. As long as we are perfectly replicating, we can fail over in an instant. And so we have a lot of systems that do replication. And so one of our design decisions is how to replicate or what to replicate. And then allocation is our job of deciding where our data should be and what fragments should exist, what replications what pieces should be replicated and where those pieces should exist. Well, the idea of fragmentation is that you have a table or an object, and it is something about which our system needs to store data. It's an entity. It's exactly like a table. It has rows and columns. And the idea is, if we, depending on our business operation need, we can either split the table by putting different sets of rows in different locations, or we can separate the data by putting different sets of columns in different locations. And so horizontal fragmentation is when we say, okay, well, these rows go here and these rows go there. The employee rows for New York go to the New York computer, and the employee rows for California go to the LA computer. Right? That's the horizontal fragmentation, by dividing up what rows go where. And then vertical fragmentation is when you assign different columns to different locations. Now, you usually have to do some duplication here, because you're always going to need the key and any foreign keys. But a lot of times you can severely limit the amount of data that you need by using a vertical fragmentation. And then there's all kinds of possible strategies. And within a particular database, you might see this type of distribution. Well, so here is horizontal fragmentation. And so what we see is that we have customers that are located in Tennessee, and their records are stored in Tennessee. Similar, customers that are from Florida are stored in Florida. Right? So there won't be any, or hardly any, network latency for someone in Florida getting customer data for Florida. And that's the idea. The idea is that the data is in the location, or at the location that's going to use it the most. Now, that doesn't mean that Georgia can't get Tennessee's data. It just means that it's not stored there. So when they want it, they get it, and they would just write a simple query, but it wouldn't actually be stored there. It'd have to be collected from across the network. Well, so vertical fragmentation is when some columns are relevant to one group and other columns are relevant to another group. Here we have the service group, which is really only interested in the customer's name, address, and their state, while the architecture group, or the collection group, is interested in the customer's limit, their current balance, and how much they have due. Right? They don't really, I guess, need their address at this point because they're not going to go get them. But you see, there's different columns required by different applications. Different processes require different columns. And if we were to split our table based on that, we would be doing vertical fragmentation. Well, here's a little example where we're doing both, right? Because we have our nodes, multiple nodes in one location. And it's just the idea that we have both service and collection in all three of our locations. Therefore, we have both. We have here, you have a distributed database with both distributed horizontal fragmentation and distributed vertical fragmentation. Well, replication is the idea that we're going to store multiple copies of our database. So much for redundancy, huh? Yes. We will have redundancy. And so we must maintain the consistency of our replicated data. And so the idea is, how are we going to do that? Are we going to push our replications out, meaning that once a change occurs, then that change is sent to all of the other locations that need to be updated? Or are we going to pull in changes whenever they occur? So like when a particular node is ready to update, then it pulls those changes in. But you can see that this process of bringing all of our replicated data up to speed, depending on how many different sites we have and things like that, might take a little while, right? So we want to have our replicants all in the same state, but we're going to let it happen. We're not necessarily going to have it all be required to happen at one instant in time. And so that contributes to complexity also. Well, so fully replicated means that we're going to have all of our multiple copies of all of our fragments on multiple sites. And that means we're going to have to spend more resources keeping all those pieces consistent. Right, so if we do fully replicate, we're going to have a higher cost in keeping our consistency. Well, partially replicated means that some of the fragments that are perhaps the ones that are used the most or are most important, so most likely going to be the ones that are used the most, we'll replicate them because remember, we're incurring a cost of replication. We are going to have to have the process of maintaining consistency across all of our things. So whenever we replicate, we need to do it with the pieces that we really need to have and that will make a difference in the way our system functions. Well, and of course, you could be distributed but totally unreplicated, meaning that each fragment is in a different location, and then when you see the database as a whole, it really never does exist at any one location. It is just logically a whole database, and it's unreplicated. So if you're not getting any advantages of replication in this case, which is sort of fault tolerance and failover capability. Well, there's also a question about how we partition our data. And so, or it's sort of a parallel idea. A centralized data allocation means that we have all our data stored at one site. Partition means it's spread across more than one site. And replicated means that it's spread across more than one site and it is duplicated on multiple sites. Well, so here we get to this idea of how long does it take for our system to come into consistency. All right, so that's what we want. We want our system. So we have to maintain consistency, even though our data are distributed. And so we have this idea, this CAP theorem of consistency, availability, and partition tolerance. The point is that we want to have our systems do this, but we know that we can't have it all at one time. You remember our ACID framework, right? Where automaticity, consistency, isolation, those ideas are lost now, right? And so we have a new idea called BASE. Basically available, soft state, eventually consistent. And this is the idea that when we have replication, we are going to have our changes eventually bring our database into perfect consistency. But we're going to be willing to live with it out of consistency for some part of the time. And this is a different way of looking at the world, but in many situations it can still work. And it's a sort of an evolving way of looking at a system. And so the centralized systems and relational distributed databases, they can still support the full ACID model, right? The complete ability to do database transactions. As you move down this hierarchy, you get to the point where consistency isn't all that important. Like in the Hadoop world, where you can have terabytes of data, the perfectness of any 1 megabyte of data is much less important. And so you can use this different approach to ensure your consistency and integrity, but you're going to get some sacrifices. But usually in the type of systems that you're working with, those sacrifices aren't important in terms of effectiveness of your system. So you're making a trade-off of more efficiency. You're letting things happen slower, but you aren't really hurting your effectiveness that much. Well, Hadoop systems or NoSQL systems are very interesting, and they are evolving to handle the new types of social media, web-based, text data, images, things like that. And they're totally different than any of the kinds of databases that we've talked about up till now. They're not transaction-oriented. They're not going to have to worry about keys and foreign keys. So let's have it. So the high volume example is, so suppose that we have 7 million tweets on the election from last week. Now, we don't really care that much about where those the relationship between one tweet and another tweet, right? It's not like a key, foreign key kind of thing. Right, so now we have those 7 million tweets. We've written them once into the database. Well, once they've written in there, they're never going to change again. They were tweeted last week during an election, or 2 weeks ago, whenever. So you write it once and you read it over and over and over again and process it many different times with many different keywords and things like that. And so that is the idea of write once, read many. It's something that's not going to change. Doesn't matter if it does change a lot of the times, but usually it's not going to change. And then this other idea of streaming access, that's just sort of the magnitude of data. You have all of the Facebook posts that happen today. And then tomorrow you have all the Facebook posts that happen tomorrow. And then your program is to process those in some way. Well, you can see that's a lot of data. And so you have to have efficient ways, and what we do is parallel processing. And that's what move computations to the data means. It means that instead of bringing the data to the processor, we write processes that can go to the data. The data are far too large to move from one place to another, so we have to be able to transport the algorithm or the processing to those sites where the data are. And fault tolerance, that is one of the real strong aspects of these systems, is that the way they work is sort of naturally fault tolerant because of the level of data that they deal with and the kind of redundancy that exists across their processing. Well, here's an example of a simple Hadoop cluster, and we have a Hadoop cluster on a project that I'm working on with NSF and people from computer science, where we are building archives of different disaster events. Well, all the web pages and all of the tweets and other types of information that comes from a disaster. Well, and so the idea is that we have these data nodes in our cluster. And then what we have is we have a client node that wants to do something on our cluster. And so what the client node does is it makes a call to the name node and finds out which data nodes have the ability to do its task. And then the client node sends the message to each of the data nodes to do the task that they want, and the data nodes do that task on their data. Then the data are combined, or then what the client does is take the data that's returned from each of the data node and then combines it in a one final step to sort of aggregate or reduce the results to the final set. And that's sort of how the Hadoop idea works. And in the ACIS5504, we have a really good section on this, and we're going to be improving it in some really cool ways in the coming semesters. The replication in terms of Hadoop is the idea that you're going to store a particular block of data. And remember, these blocks are much bigger than a normal block size, where we might be 512K block on our computer. These might be 64 megabyte blocks. But here the idea is that if you can specify how many different times you want the data to be redundant, to be replicated. And this is what gives us our fault tolerance. By replicating this data around our different data nodes, we have the ability to ensure fault tolerance in these systems. What's really interesting about it, though, is the parallel processing of the client node, and how the client node can execute the same process on each of the data nodes that it would execute that it would execute on any one node. And that's the idea of pushing the processing down to the data node. It's the client node that sends the process to the data node. The data node then executes it. And these processes are often very, very simple. Like I say, we have a really good segment on this in ACIS5504. Well, finally, we come down to the commandments for distributed databases. You know, the ideas here are these. If to be the perfect distributed database, you ought to be able to have these characteristics. And the ones I think are most interesting is that you shouldn't have to depend on any other central site. That we're doing this a lot often for failure independence, because remember we're spending a lot to be able to have a distributed system. So we have some very important needs, or we wouldn't even be here. Some ideas of like fragmentation transparency, I totally support those, and some of these things like database independence. You know, I don't think we're really there yet. Well, in summary, the distributed database is just the database in multiple geographic locations, whether it is a part of the database in each place or the entire database in each place. That's what distributed database is, and then it's all connected via the network. Well, distributed processing is putting the program in multiple places. Distributed database is putting the data in multiple places. And every distributed DBMS has a transaction processor that has to manage all of the processes that need to be executed, and then we have the data processor, which that serves the transaction processor with the data that it needs. Homogeneous distributed systems are ones that are used just one DBMS, just one vendor. Heterogeneous means that we have a distributed database system where there are multiple DBMSs involved in our architecture, right? We have Oracle in one location, SQL Server on another, and we are merging those data in our application. Finally, the most important or most interesting things to me are the data fragmentation and replication strategies. All right, well, I hope you have a nice rest of your day.